take a look at the homework. You're supposed to do 38, no, 98, 99, 100, 101, and 102. Okay? 98, 99, 100 you're supposed to try without a calculator. 101 and 102 you could have used calculators. Okay? Are there general questions? You want to do one of them together? Just to reiterate what we did last time.
100.
I should do 100 and
100.
99.
100.
Christian, shut up.
100.
99.
You guys okay? You guys okay? Huh? Attendance.
I don't know.
Yeah. I'm sitting here just looking at it.
Paper's vibrating when you move it on.
Really go over
Paper's
here.
vibrating. You doing it on paper?
Oh, one of the grips is probably coming off. My list wasn't. Yeah, actually, this is one before this.
No big deal.
For some reason, you're a profile.
Quickly, let's take a look at number 9. 99. 99.
Why?
Why 100? What's the difference though, honestly?
The difference is that it's 1 greater than 99.
What's the difference in the problems? It's the same problem.
You guys okay? You good? No. You guys need some counseling?
Are you okay?
Huh?
Why are you okay?
I don't need counseling.
Kenny,
Yeah.
why?
Are you recording?
Yes, thank you.
Upstairs with the sofa.
Alright, so if a problem asks you, and it tells you that the velocity function is given by the following, and it says, find two things. Find the displacement and find the total distance traveled by that particle. The displacement first, and the total distance traveled. What is the displacement always going to be?
Interval.
Just a regular integral. Okay? So displacement, your answer is simply the integral of t cubed minus 10t squared, go get some more, plus 27t minus 18 dt from 1 to 7. Okay? That's the displacement. Now, whatever you get as a number, that's your value. Remember, how do you integrate this? t4 over 4 minus 10t cubed over 3 plus 27t squared over 2 minus 18t from 1 to 7. Again, there's no constant here, there's no c, because we're given our lower limit of integration and we're given our upper limit of integration. We'll talk today, today's lesson is about how to find that c value for those other conditions.
Yeah, I was just gonna wonder because I was wondering because when we were doing these problems, we never added on a c after integration.
Because these are definite integrals. Remember, indefinite integrals where we don't know where we're going from where to where, that's where c comes to play in. And we're going to talk today about it. Whenever you're given an interval and you know where you're going from where to where, it's not going to be indefinite integration. It's definite.
But can it still move up and down in that range?
No, because Kenny, this is definite integration, which is what we're doing right now, is really asking you, what is the area? That's what it's doing. It's not asking you about moving and stuff. The other one with indefinite integration is saying, like, find a family of functions that represents the integral of this, and there's several answers. That's where the c comes in. Whereas this is really saying, what's the area? Okay? Now, this part is simple. What do you do here? Plug in what? 7, you get a number. Then you plug in 1, you get a number. Subtract the two from each other. Okay? Did anybody get the numerical value for this? Anybody get the numerical value? Exact answer.
You asked the question.
No one got to this? Come on, guys. Don't just stop when you get to the integral. All right, well, a simple way to check, here's what I'm going to do. I'm going to type in the original function in my calculator. Okay, but I'm checking because you guys didn't do the work for it. Again, I assume you're going to do the work, but if no one does it, I'll check. T cubed minus 10t squared. So I start with x cubed minus 10x squared. Thank you. Minus. So that's the original function. That's the velocity function. We showed that we want to integrate it. So second, calculate. Number 7, the integral. Hit enter. It's going to bring it up here. Come on. Or my calculator's going to freeze in the middle of it. Awesome. Great.
Okay, I got it.
Something wrong with this program. I gotta fix this. I gotta reinstall it. Something's been happening lately. All right. It's frozen.
No, I don't look.
Yeah, that is.
But it's actually frozen. I know it not look like it's frozen. Every command is not working. The program. The function was this one right here, up top. So type that in. Press second calculate. Press the number 7 for integral. Enter 1 as your left limit. Enter 3 as your 7 as your right limit. Hit enter, it'll shade it all in for you. Can I see yours when you're done? You got it ready? Look like this? Does yours look like this? Check yours. Again, guys, we're not doing this for my help, for Christian's help, for Yvette's. Everybody should be checking on their own. So, what you notice is this. The integral, in this case, the integral turn out to be? It looks like 0, actually. It says 4.8 times 10 to the negative 13, which is 0. So you plug in the 7, you get all your numbers, you get an answer here. You plug in another number, you plug in the 1, you get all your numbers. You subtract them, you're going to end up getting 0 for this problem, for the displacement. So what does that mean, Edgar, when I get a 0 displacement? What have I done? I've completed some sort of a cycle. I've returned to the initial.
So you got a sign graph?
So, it could, and a very good example is a sign graph, absolutely. If I start here, and I walk around, and I walk around, and I keep going around, but then I end here, I have no displacement. So since this gives us 0, that's our example here. Did you not get 0? Is that what you're showing me? No, you did. Okay, look at the bottom for those that just did the integral. You see e to the negative 13? In scientific notation, it means times 10 to the negative 13. So what it means is this. 0.000000000048. That's what the number is for the integral. Now, the calculator uses a technique called numerical integration. It doesn't actually do the integral. See how we do the math with the integral and we get an answer? It does an approximation. It uses LRIM and RRIM, but a much more advanced version of that, called Simpson's method. Okay, Simpson's method is what it uses, which takes like trapezoids, rectangles, different shapes, and it approximates it, but almost to the point where it's exact. So you see how this looks like it's 0, and it says almost 0, look at that number? It pretty much is 0, okay? That's our displacement. But now, looking at the graph here, I can clearly see that I'm not going to have 0 distance, because I have to add together all these areas now. This is considered to be a negative area right here when I do the integral. But we know that when I do the distance, you think of it as a positive. Thank you. So I have to use the absolute value of all my partitions. How do I find the partitions? Using synthetic or finding the roots or zeros. Roots or zeros. So you go to the original function. You want to find the roots of it. So I go ahead here and I write in 1, negative 10, 27, negative 18. So again, before I do the distance, I do this. I start with a 1.
Wait, don't you also start at 1 because one of your like limits? Not limits, but I mean as in no. Yeah, domains. Yeah.
You can say limits. They're limits. That's fine. So when I type in this, when I write this in, I see I'm going to get 1, negative 9, 18, 0. So this means this is clearly a root. So that's going to be one of my partitions. But that's not a problem, because doesn't the actual thing start at 1? Coincidence, Kenny. Coincidence that it's a root. It doesn't have to always start at 1.
No, I know, but it's just like the last 3 problems that we've done.
It happens to be, yeah. So after this, it becomes x squared minus 9x plus 18, right? I'll bring these down. What does that factor into?
X minus 3.
Awesome job, Kerry. So I get 3 and 6. So I know that I have roots at 1, 3, and 6. So that means that I need to separate this into 3 parts. Or, well, yeah, 3 parts. Because remember, what's my interval? My interval is really 1 to 7, right? So I got to do the integral from 1 to 3, absolute value of v of t dt. That's the first part. Now, even though, Jasmine, can I see yours? Even though the first area is positive, I'm still putting the absolute value down because I don't have the calculator on this part. Remember, you can see that it's positive and then it's negative. So really all you need to do is absolute value around the middle part we're going to do, which is from 3 to 6. But again, do we really know that that's negative? No, we don't. Okay? So use the simple way and put it around all of them. John, can you finish your verses? So write all 3 of the parts. Remember,
Yeah.
up to 3, 3 to 6.
Three. Oh, it's 6. Right.
Yeah.
6.
How do you see you call? Anybody? Oh, you know what? They don't call me.
What is this VT, right?
Sorry, VFT. Good. Your last part?
Would it be 6 to infinity?
Oh, don't forget, we're starting at 7.
Oh, sorry.
And remember to put around it. Very good. Absolute value. Now, be careful with the absolute value. Just put it around the whole thing, please, so we know the whole thing is absolute value when you do it. Okay, around the whole thing. But the idea is the same. Okay, what's that?
The first one.
Sorry, around. I don't mean the whole thing. I mean the VFT part. As long as around VFT, you can do this way. You can do this way, but you can't just put it around DFT. Just be careful there, okay? Because the absolute value, you're really looking at the function's absolute value. So either you can put it around the whole thing, or you can put it here. Either of those are fine, but not just the dt. Because absolute value of dt doesn't tell me that much, actually. It's the function that we want. So either do the function alone, or do the whole thing. Okay? Again, it's always positive.
One, you know how it's like 1, like,
The same thing. Just 7 and 6.
Where's the 0 to 1 you're saying?
well,
Yeah,
usually,
look.
you know, it has 1, so that 1 doesn't really have an upper, like, 0.
No, please ask. I'm trying to...
Because you know how, like, 3 and 6 have, like, you know, in limit, I guess it's because of 1 to 7, but actually, like, I thought it was, like, 0 to 1.
You got to start with your
Yeah,
lower
that's what
limit.
I'm saying.
Yeah, start with the lower, and that's always the beginning. The last limit will always be the end. And then whatever's left over, the 3, 3, 6, 6, comes from the roots in between. Okay? So even though 1 was a root, 7 wasn't a root. We still ended 7, we still started 1, but it's the roots that are in between 1 and 7 that matter. So the 1 really didn't matter at all, actually. Technically, it doesn't matter one bit, because you know you're going to start at 1 no matter what, because it's starting at 1. The 3 and the 6 are indicating the roots in between. And remember our rules of integrals. 1 to 3, 3 to 6, and 6 to 7 all together really give you 1 to 7. So that would really get back to displacement, except for the fact that we have absolute values. So you need to do this integral, you need to do this integral, do this integral, make them all positives by hand, and add them all up. And what are you going to know? Your distance traveled is always what? Larger. Always larger.
Oh.
Think of a simple example.
Positive.
Sure, absolutely positive also. Simple example is walking in a circle. You have a distance traveled, but you have no displacement. The distance traveled will always be, and now again, it will always be larger than or equal to, because if I walk from right here to right here, my displacement is 3 feet and my distance is 3 feet. It's the same. So you could have the same if it's always a positive movement. So if I gave you a function that looked like this, and I said this is the velocity function, Edgar, and I said from A to B, what conclusion can you make about the displacement and the distance? They're equal to each other. Because the displacement, remember, is the integral from A to B always. But isn't that area already all positive? So even if you do the distance, aren't you going to do the same thing? Because there's no roots here. If there are no roots between them, then they're going to be the same, unless it's below the axis. If you have this kind of a graph, like this, where V of t is represented down here, and you want the integral from A to B, well, the displacement will be a negative number, won't it? The displacement is negative for sure, because that's a negative, it's under the axis. But the distance will be, it's going to be the same answer, though. Numerically, it's going to be the same answer. Because, again, this is the displacement, it's all negative. How do you find the distance? You take whatever's below the axis, don't you make it positive? So if you get an answer for displacement for this one,
How the displacement doesn't be the same, distance also has to be positive.
but no, I'm saying the numerical value is the same. The displacement is 70, where the distance would be 70 also, but one is negative, one is positive now. Okay, whereas here, if you had a displacement of 50, then the distance would also be 50.
What does always work with that?
And it always does, always, always, always. And here's the way you can write it. If, here's your law, if V of t is always greater than 0 for all values of t, if it's always greater than 0, like this example right here, if it's always above the axis, then
Yeah, that's what those problems get in.
Okay? If it's below the axis for all values, then they are what of each other? Opposites. Again, if the function is always below the axis, then displacement and distance are opposites. Okay, displacement and distance are opposites. We're doing really well with integrals, guys. Keep it up, please. Seriously, this is really encouraging. This is tough stuff, believe it or not. This is the stuff that is on the AP exam. This kind of question right here, just like this. Okay. Now, one thing I want to give you guys a heads up about. I'll give you a minute to copy because I know some of you are writing. Your topics that we're looking at, we've already started. Like this topic is actually under applications of integrals. I didn't realize that I put it under there, even though, like, you know how I split it up to limits, derivatives, derivative applications, integrals, applications of integrals? This is really under applications of integrals. This is really the next chapter. But we already did this, which is great. Remember the average value theorem? Yeah. Where we did 1 over b minus a times that integral and stuff? Where we did the example of like a cup of water, when it settles out, it flattens out? That's also applications of integrals. I don't know. I thought they were under regular integrals for some reason. But that's the topic it's under. So we're already ahead of that last chapter, which I'm very happy about. Because the last section, applications of integrals, the other ones, where we start looking at like volumes, where imagine if you took like,
Oh, I saw this in the textbook.
yeah,
Somewhere.
imagine if you took like a piece of paper and rotated it 360 degrees. What would the volume be? What kind of shape would that be that it results in? A cylinder, right? Take this and revolve it. If you actually look at it, isn't that a cylinder around the whole thing? It's a cylinder that's 3 dimensions. That's when it's going to get tough. That's the hard applications of derivative or integrals.
Well, I was saying it's funny because those other classes, which are AP classes, which are way behind us for some reason.
Are there some that are?
There's some that are.
Probably in other schools.
Yeah,
Yeah.
I'm just saying there are some. I'm just
Oh.
saying there's some might have funny.
There's some that are ahead though too.
Yeah, I know, but there's always some that had it.
It's always, yeah. I told you guys the example when I was in AP Calc, when my teacher did. He was insane. I mean, we had 30 people in class, and he was done the whole year by middle of February. But he went so fast. Like if anyone, he didn't answer questions literally at all. It was the kind of teacher that was, I mean, it was a good teacher if you were really smart and you understood everything automatically off the bat, which is not most people. Like literally, like imagine I said something once and I would never repeat it again. That was the kind of teacher it was. He went through it so fast. And in addition to that, I mean, he also been teaching for like 60 years, so he knew exactly what topics to cover, exactly how, you know, how much emphasis to put on them. Whereas for me, it's the first time teaching this. So it differs with your teachers. Yeah.
They're on slope fields, I think.
What's that?
Slope fields.
They're on slope fields?
Yeah.
Well, today we're going to revisit slope fields and use them in integrals. Remember for slope fields, I gave you guys those problems, and there was a part C that we couldn't do yet?
Yeah.
We're going to talk about how to do that one. Okay?
Indefinite?
Is that indefinite? It is indefinite with an initial condition. And we'll talk about what that is. Or a particular condition, but it is indefinite, yes. Where you're finding that C value.
Wait, but isn't it the same thing?
No, and I'll explain. Let me explain now, okay?
I'm so confused.
So here's what we're going to do now. We're going to look at indefinite integrals, which we've done already, which is just the integral with no numbers, so the plus C, but with particular solutions.
What?
I'll explain.
What is particular mean?
I think I'm asking what solution.
You don't know that?
And me and Mr. Smith talked yesterday about this, and a lot of textbooks do not name this correctly. They always write indefinite integrals with initial conditions, which you could have, and I'll explain what that means, but really it should say particular solutions.
Can I ask you a question?
Yes.
What do you know what's correct?
How do we know it's correct or not?
Well, yeah. You
Because-
said it's not correct.
No problem, because initial conditions are a type of indefinite integral, but there are other types to use. So you can only look at initial conditions, but the general category should be named particular solutions. It's weird. I'll explain. I'll show you the difference with an example.
My goodness.
So if we,
I don't want to lose myself.
okay, if we looked at, let's say, g of x, and I told you g of x equals x squared plus 2x minus 4. Okay? New topic, yes. And we've done indefinite integrals already, but now we're going to look at particular solutions. Tell me what the integral is, please. So I want to know, what is the integral?
Over 3 plus 2x. The x squared. No, yeah, x squared. Yeah, x squared. 2x minus 4x.
Good, and most of you noticed, these twos cancel, right?
Yes.
Is that it?
Yes. That's it.
Are you sure it's it?
That's it.
Plus C.
Thank you. There it is. Again, this becomes x cubed over 3 This becomes x squared over
Plus C is
2.
understood,
The
okay?
2's
It's
cancel.
like
The negative 4, this is really x to the 0. Remember, it becomes x to the 1 over 1. Now, remember, there's a plus c at the end here. That's the key. And we talked about this the other day. If you're given the limits here, you then evaluate. You put the bar at the end and you evaluate the limits. But when you're not given the limits, that's why it's called indefinite, because I'm not definitely sure what's going to happen. We talked about this in class with slope fields, and we talked about a family of solutions. So this solution, if c was 5, it would be the same graph shifted up 5. If c was 2, it would be the same graph shifted up 2. If c was negative 12, the same graph shifted down 12. So this graph, whatever it looks like, I'm not going to make believe I don't know what it looks like, but let's just say that the graph looks something like this. That's the general shape of a cubic. Based on the value of c, the graph could look like this. It could look like this. It could look like this. Like this. I mean, it just shifts up and down. The curvature doesn't change. I'm screwing that up with the curvature. It's the same graph, just shifted up and down. So to make it simple on yourself, if you'd like to, you can graph once. Yes. And I'll copy and paste this several times. So let's clone. And if you take the clone now and put it directly below it, it's the exact same shape, identical, because I just cloned it, but it's shifted up or down. So if c is one value, it would be one of them. The question becomes, how do we determine c? And that's where this topic comes about. Okay? Give me a suggestion or what you're going to say.
So like, so if you have like 5 over x, so then we do the interval that you raise it to 1 power, is it going to be like x to the 0?
5 over x, that example is one of the state cases where it becomes natural log. Because remember, the derivative of natural log is not 1 over x. So if you start with some number over x, that integral is going to go back to natural log. So be careful there. We'll go back to that. But the idea here is this. How do I find out what the c value is? Well, take a look. Go back at the last example. This is the integral, isn't it?
Yeah.
This is the actual integral. If I tell you this, though, if I said to you that, for example, the integral of, or no, I'm sorry. If I tell you this, if I tell you g of 2 is equal to 4, what does the capital G mean again? It means the integral. Good. It means the integral. So here, if I tell you that g of 2 is 4, this means the integral, you want to write this in words probably, okay? I would write this out like this and then write what I'm saying right now. The integral, when evaluated at x equals 2, is equal to 4. Again, this statement right here means the integral of g, that's what capital G is, when evaluated at x equals 2, that's the 2, is equal to 4. Again, the integral when evaluated at x equals 2 is equal to 4. So, to determine the c value, you know that x equals 2 now, right? Plug in 2's in the x spots, set it equal to 4, and solve for c. That's it for particular solutions, literally, that's it.
Wow.
It gets more complicated with velocity, and I'll explain why, but that's literally the whole thing. And I call it a particular solution because this solution is particular to this condition. A lot of books call them initial conditions. Initial conditions only exist when this happens to be a 0 here. So for any other number, it becomes what's called a particular solution. So a lot of books call them initial conditions because traditionally they'll give you a 0 here and they'll give you the number. And that is the initial condition. But if I give you a 2, it's no longer an initial condition, it's a particular condition. So my answer is particular or specific to this condition right here. This constraint, if you will. This is like a constraint if you want to think of it that way. So if you want to find the c for this function, what I'd like you to do is go ahead, and I see your hands, those that are ready to do it, go ahead and plug a 2 in for x, set it equal to 4, and try and solve for c.
Just a random number.
I told you this. This is going to be given, correct. This is not something that you have to determine here. That's going to be given to you. And we'll explain how you can apply that to velocity in a minute. So again, plug in the 2 for x. Plug in the 2 for x. So you have all your 2's in for x's. You have a c at the end over here. Plug in all the 2's and solve for c.
Yeah, y next, just find c.
Exactly.
Yeah, no, I don't have a question. I was just wondering, for c, do you have to have a particular solution to find c?
Exactly. Exactly. Always, always, always. You can't get c unless you have some sort of other information. Because look,
So,
you've got an unknown variable, don't you?
Yeah.
You need to know the conditions to get that unknown variable.
And
You know it's not a variable c, it's
yeah,
constant.
it like in an application of a particular,
We're gonna do it in a second. And you wanna ask first?
I was just asking if any kind of.
Velocity and acceleration. Initial velocity given, final velocity given, remember physics? So if you're given that information, that's how you can determine the actual position function. Because you can integrate velocity. If you don't know from where to where, if you integrate it, you get indefinite integral plus c for position. But you want to know position function, you plug in your initial condition about your velocity into there. Okay? So here, I know you're all doing it, I'm going to plug it in also. That's what I get when I plug in my numbers. I hope we got the same thing for at least the fractions.
Yeah, I'm saying, I just don't know anything about it.
Okay? Really?
It's like 2.666. Yeah.
Just look at it. It goes in twice, there's 2 left over. Okay? So 4 equals 2.6 repeating, minus 4, plus c. Move negative 4, and 4 and negative 8 give me negative 4. Move over the 4, this becomes an 8. Equals 2.6 repeating plus c. This is where it gets mixed a little bit tricky. Subtract it. What do you get?
You get 7.4.
5.3.
5.3 repeating. Subtract this.
Okay.
Combine these two to give you that 4. Add 4. Add 4. Now when you subtract this, remember, what's 2/3, guys, as a decimal? 2/3.
0.3.
2/3. 0.666. What's 1/3? 0.333. Whenever you subtract the 0.666 from a whole number, you always get a 0.333. What do most people put? 0.444. Because they think, oh, 10 minus 6 is 4, right? But you're really subtracting 2 and 2/3. So subtract 2 from 8, you get 6. But you got to subtract another third, so you're going to get 5 1/3 here. Or 5.33333. Jasmine?
Because the interval was initially this, right?
Good.
Okay, so then don't you subtract that?
Oh, you're missing here. This 2's canceled, that 2's gone.
How about this? We put
This, no, this is 4 here. Those 2's don't cancel, those 2's cancel. So you still have to do 2 squared here.
right,
So
so
we're
it's
still
4,
being-
right?
That's 4. So right here is 4. These 2's in the integral,
The concept
those
is
cancel.
easy, but when you start applying it to like formal things.
So you're left with x squared. So you have to do 2 squared here. 2 squared is 4. Then I did 4 minus 8 to give me a negative 4. And I resulted those to be negative. So then I did 2.6 plus negative 4. Again, I took these 2 down, right? It doesn't matter what order. At this point in time, go ahead and type in 2.6 repeating plus 4 minus 8, get a number for that, and then subtract it over here. You'll get this answer. But I'm just combining terms in a weird way.
What do they,
So basically, like based on the giving, for like,
You find C, exactly.
So-
Based on the given only.
so C could be different basically.
That's why it's called a particular. Particular to this condition. Again, guys, C could be any number. If I gave you a different value, if I said G of 2 equals 5, then C is going to be different. Or it might be different. There is a chance it could be the same if it's coincidence. Again, this answer for C is particular to the initial condition or the condition we were given. Ours happens to not be an initial condition. Initial conditions are really when you have a 0 here. That's the mistake in the books I was telling you about. They call them all initial conditions when this is only initial condition if there's a 0 right there. Right here.
Maybe any instance where we have to find that condition or constraint to then find C? Or would we be
Let me think about that actually. Hold on. Could you be given?
in real world, yes. Actually, that I did. When we played in real world.
I'm going to say no right now with these problems, especially on the AP exam. They're going to give you the initial condition for it. I'll try to look for an exception to that, but I can't see that happening. The only time I can see that happening is a real world example, like you can measure the start velocity of something. Okay? That's where I can see it happening. So here's what I want to do. And this problem is where it gets tough. So I'm going to do an easier one, and then we'll do an AP problem that looks like it. Okay? So let's start with an example. I'm telling you that the velocity is given as 2t minus 3 cos t
It's like the question that we
and
have, how can we steal more American money?
x of
The $1 million question.
0 equals 4.
So this is not particular anymore.
Fine, now this is, it is particular, but specifically it's initial condition. It is particular again, because I'm giving a number here. I'll explain.
No. Yeah, it.
Okay.
Oh, okay.
It's not a question mark, it's really your answer.
Is capital V equal to XT?
Sure, capital V is, absolutely, but that's not capital V, that's lowercase v.
Really?
Sorry.
No, I mean, I'm just saying, like, in different.
Just to be clear, guys, that's a lowercase v there.
We're doing
Like,
like.
if I wanted to say that, like.
So G, that is your condition you're given. This is the integral in a sense. yes.
Oh, that's okay.
That's what I meant.
Wait, so x is, wait, shoot, so we're going back. Because, wait, no, wait, velocity is,
Yeah, it's
velocity is
going
the
back.
second. Is velocity the second?
You're going back up, you mean, back up.
Yeah.
Okay, I think we said back,
Wait,
down.
why would you want to take every time?
So let's go through this, guys. You're given what function?
Wait.
V of t, which is a wave, good. And what do we call v? It's the original velocity or the original function, okay. And what are we asked to find?
Position.
The position. We're asked to find the position. Remember, this is position. This is velocity. Now, we can start by integrating, and then we'll see what to do with the condition we're given. Okay, we'll see what we can do with that in a minute. So let's take the integral of this. We say, okay, x of t is really equal to the integral of v of t. Remember, I need a dt at the end here. Don't forget your dt when you're doing this stuff, guys. Especially if it's part 2s. You got to make sure you write all your other stuff. You do. Okay? Because this tells you that the position is the integral of the whole thing. If you put the dt here, then it's only the first part.
But if you were already integrating that whole thing, why do you need a dt?
Because dt tells you what you're integrating with respect to. If you don't have a dt, I don't know that t is the independent variable now. X could be the independent variable, g could be, f could be anything, right? This tells me what the variable is I'm looking to integrate. So integrating 2t, which I keep doing that. Yeah, you're going to get t squared, 2t squared over 2.
Minus 3 sine.
I keep doing that, I know that, sorry. Integral of cosine is just sine, positive. So I keep the negative, I keep the negative, but it's just,
Okay, yeah. I was
Then we put x get 0?
okay? Plus c.
No.
Okay, now we're gonna use the 0, Jasmine. Now we're gonna use that 0.
You use 0 versus 0.
For,
It's going to be 0 plus c equals.
because I did sine instead of
4,
cosine.
so the thing is what?
So c comes out to be 0, that's fine, that's not a problem, let's discuss. So, we're told that the position at time equals 0, the position of the function at the initial condition is like 4 meters. So it's like starting at a cliff 4 meters up, that's what this problem is like. Okay? The initial condition is that it's 4. So when you plug in a 0 here, this comes 0, right?
Yeah.
What's the sign of 0 also? It's also 0. So when you plug in a 0 here, you get 4 over here. So you're going to get 4 equals 0 plus 0, sorry, minus, not plus really, not that it matters, plus c. I just want to show you the steps. Again, plugging in the 4 for the function, the 4 goes in over here, because that's the value of the function. This is the location of the function here. I plug in my zeros, I get c equals 4. So your actual answer for this problem is this whole line right here. Repeat this, please, but put a 4 in for c. So what is the function x of t? X of t is. That's the actual answer.
Is there no way to represent that given? So we found that at the particular.
We found,
Well, we
yes.
found that at the particular. So is there
Correct.
no way to write that in the end that this is the answer at a particular point?
This, you could write in words if they ask you, like, what does that mean?
Could be, but-
But you don't have to, no. But if they say, like, what indication or what does the x of 0 equaling 4 mean? It says, well, this is the answer when the position starts at 4. Again, remember, when time is 0, it's the starting time, isn't it? So this means it starts at 4. That's why it's called an initial condition. As opposed to the last problem, we had a number here. It was a particular condition. This is still particular, but to be more specific, you can call it initial. Okay? But you don't have to do that again. You don't have to write or anything like that. Okay, so again, C turns out to be just 4. That's an easy example. Where might you see this kind of a problem, guys? No, obviously physics, but on the text. Sorry. On the exam. Multiple choice.
Yeah.
Multiple choice. What else?
No calculator.
No calculator. Definitely. Come on. Did we even go near a calculator here?
Yeah.
We didn't have to touch it once, the whole problem.
I did it.
Okay?
Yeah, I didn't know what 2 divided by 2 was.
Now, let's get to a tough example now.
Right? If I need a calculator.
And I want you to think for a second. Think about this part of the problem. If I give you the acceleration, and I want you to get to the position, what do you have to do?
We go 2.
Integrate how many times? Because you integrate the velocity, then you integrate the have to get position. So how many particular conditions are you going to have to be given? 2. Because remember, when you integrate to the velocity, don't you have a c for velocity? You got to find that c, then integrate that, you get another c in the position. Find that c. So if you have to integrate twice, you need 2 conditions. Whether they're initial or particular, I don't care. Doesn't matter.
Why would you need the first one? Okay, no, I see why. Okay, never mind.
Let's do it, but you see it now, right?
I see why.
Okay.
You don't have to memorize like acceleration.
You have to know that, yes,
So
absolutely.
it's position, velocity, and acceleration.
And then for integral, you work up this way.
X.
Let's say a of t equals
I mean, it's
Two.
X, Christian. Shut up. I don't
t to
want
the
E.
third plus
X. I'm not being stupid.
5 minus, or let's say plus cosine t. I'm using cosine right now because whenever there are integral problems with velocity, position, and acceleration, they always use trig functions. The AP exam uses them left and right, so I want you to get used to it by now. Okay, it's always going to be used there.
Is that 5
Yeah,
or 5G?
that's
Should be a 5. No, it's just a 5. Just a 5.
5?
Yes. 2, because I thought we were going to integrate it twice, so it's going to get up to being t squared eventually anyway. Okay, this will become t to the 5th eventually, right?
That's fine.
Okay.
And-
Well, we're not. You can't do anything yet. I didn't even ask the problem.
No,
You
I
can
know.
integrate, you can integrate into it.
How do you know I was asking you for? What if I was saying find the derivative of acceleration?
We're not-
We're
We don't know what
doing-
comes after acceleration.
We don't know
That's
yet.
not doing this, that's not right.
Jerry.
I'm working hard.
Yeah, here, Jack, shut up.
And plus, you already asked us that you were already asking.
All right. I know, Kenny. Please.
Temper tantrums, man. Jeez.
Well, you know what?
I can't believe you said that. I feel like slapping me for calling me Benjamin Button.
That's okay.
You already said you called me Benjamin Button. So for some reason, I am.
If a of t equals 2t cubed plus 5 plus cos t, find the position function if x dot, that's x dot, by the way, the dot's a little too high, it wouldn't be that high. If x dot of 0 equals 4, and x of 0 equals 5. What is x dot, everybody? Velocity. Remember, Newton's Newton. Newton and Leibniz disagreed. The dots indicate a derivative for Newton. So this means the derivative of position, which is velocity. So you're giving a velocity initial condition, and you're given a position. Remember, please, whenever you see this on your test, rewrite this in your mind like this, so you know what you're actually doing for that. Don't use x dot. Think about it that way. It might help you. Okay? These are both initial conditions because they're both zeros, yeah. So we're working on it.
I don't have the first one, I'm gonna assume that the zero is the same thing before.
Sine of 0 is 1.
Right?
No, it's
Good. You end up getting c equals 4. That's right. When
Okay.
you plug in a 0, that drops off, that drops off, that drops off.
This is my equation.
That's a t, by the way, not x. Now, what is that the equation for?
0. Oh my god.
Sine of 1 is like a number.
Sine of 0 is 1.
Yeah.
What?
Sine of 0 is 0.
Sine of 0 is 0.
Okay.
Sine of 0 is
I'm
0.
smoking weed.
So, is it
Because
What are you starting with? What are you starting with?
Sine of 0 is 0. We just did it.
Okay, calm down. So c equals 4.
And you did one integral, right? So this is your velocity.
Yeah.
Now, if you want position, what do you have to do to that?
integrated, but I'm asking with this two integrated.
Yep. And now this is part of the function, so this is going to become a 4t at the end. Think of it as like 0.5, 0.5 notes. You can do that.
That's not it.
Okay?
It doesn't give us
So the general velocity function, as many of you noticed, comes out to be 2t to the 4th over 4 plus 5t plus sine t plus c. Okay, everybody got this? You reduce this to 1/2 here. Now, what you're going to notice, and several of you already got this, C turns out to be 4 again for this one.
Yeah.
Because I gave you the same condition. Again, the velocity at 0 equals 4. So plug in a 0 here, a 0 here, a 0 here, plug in a 4 over here. You're going to get 0 plus 0 plus 0 plus C equals 4. So C equals 4. That's only part 1. Hold on one second. So I got V of t equaling, and I'm going to write this now. Watch what I'm going to do here. I can write this as 1/2. I'm going to write it as 0.5 t to the 4th, because to integrate that, it'll make it easier for me. Plus 5t plus sine t plus 4. Remember, now what do I want, Kenny? What's the next part I'm looking for?
You want to get to position.
So what do I do to this?
You got to get the integral of it.
Very good. So if we integrate this now, if I want the general position, I'm not using the condition yet.
5 t to the 5th over 5.
Which, by the way, what is 0.5 over 5?
110.
1/10. Very good. Those are quick numbers you gotta know. Anything where it's like 0.3 over 3, 1/10. 0.2 over 2, 1/10. Always, always, always. Because this is a tenth of this. Next one.
Plus 5 over, yeah, so good.
Well, plus 2.5 x squared.
Nice. Okay. T.
Plus t.
Again, people, this is really what? This is really 5
Close t.
over 2, like that.
That would be minus cos t, right?
Okay. And then minus cos t. Good.
Plus
Plus
4t
4t
No.
plus 5
plus
Plus c.
t.
c for now. And then we'll figure out what that is. Now, be careful here. It's not 5. Everybody, don't jump to 5. Because this cosine of 0 is actually 1. So this doesn't drop off this time. Remember, yeah, you're going to end up getting 6 in this case. Let's show why.
Add 1.
Not always. It doesn't always. Just plug it in. Don't assume that you can add 1 or just subtract 1 because it's going to change. So everybody take a look. 0 and 5. So I go ahead. I put a 5 here. This becomes 0. This becomes 0. This becomes minus 1 because cosine of 0 is 1. Plus 0 plus c. Move the 1 over. C turns out to be 6. So the final position function, this, by the way, this is a part 2. This is what they put for free response. If you can do what we just did, it's like a guaranteed 10 points right there. Okay? This is a part 2.
How do I apply this in like?
Well, we can talk more about that, but this is velocity position. It's used all over the place, but for now, do you understand what we're doing at least, Kenny? Okay?
It's just me understanding how it works in life.
That's why God created it.
Notice how I'm writing this, people.
It's just like you don't know the math, but you don't know how to apply something sometimes. It's just like when you get into those fields.
Doesn't matter, but I'm just showing it in a different fashion. Okay, so if you're taking this as a multiple choice or something, okay, if you're giving this as a multiple choice, you might have to find this function. If you wrote 0.1 in front, it's the same thing. 2.5 in front of here is the same thing. So be careful when you get your answer that your choice might be actually correct. And it might be, they might have switched the order of these two also. Cosine t might have just been put on the end. And they might put the 4t and the 6 before it.
So you have to write
The
out
test here, if we skip that middle part.
Nice.
What do you mean?
Hey, Dad, you get the right answer.
Yeah, that
tricky.
all three.
If you can do it in your head, then do it in your head, sure.
Against yourself.
Yeah, but show where C comes from. You know? Again, if it's multiple choice, you don't want to show anywhere. It could be multiple choice also. They can give you a velocity, say find the position. They can give you acceleration, say find the velocity. They can give you 1 and say find the third. Believe it or not, this would be a long multiple choice, to be honest. I don't think they would ever do this. Here's a multiple choice I could see given if they tell you this simply, like something as simple as this. If that's acceleration, and then they say find position, and they give you 2 initial conditions like we just had, that could be multiple choice, because this is so simple. You know what I mean? You're going to constantly, it's not going to be a problem that's going to,
Seems hard to me.
right? Then we have to apply our initial condition, let's say V of 1, we'll say, or a particular condition in this case. Let's say V of 1 equaled 7. I plug in the 1 here, the 7 here. I end up getting 6.66 or 6 2/3 for C. Okay, by subtracting 1/3 from both sides. So now I know my velocity function is no longer that, but my real velocity function is t cubed over 3 plus 6 2/3. And then if you want to find the position, you do it again, take your position condition, and so forth and so on. Remember though, you have to plug in the number here. Please plug in the value you're given. Don't just assume it goes to 0. If you have this kind of a problem on the test, there's a good chance it's going to be a non-calculator, just so you know. I know I missed. It's going to be a non-calculator problem. Okay, non-calculator. How come? Calculator's not going to help you here. The calculator doesn't solve for C. Okay, there might be some programs that exist if you do the integral and you give some initial condition or some particular condition that solves for C on its own, but on the test itself, they're not going to make this a calculator problem because there's no calculator involved. Okay, especially with the math. Like this math is very basic math. You got to know that 7 minus a third is 6 2/3. Okay, without using a calculator, you got to know that. Okay.
Yeah.
Anyway, is this idea pretty clear? Are we down that so far?
Still going back to that.
Yeah.
Alright. We have after school today still. Don't forget, we have after school class. What I want to do after school today is look at slope fields and how they are applied to this. That's the real topic. So what I'm going to do now is give you 2 problems to work on. I want you to practice 2 problems. They're going to be different. Okay, the 2 problems I'm about to give you right now.
We started to get into those concepts.
No, we haven't. We should do that.
Thank you, Christian. Thank you very much.
Because what, you want you to try?
Because we're going to run out of time.
Want a definite date, which is going to fit. Yes, guys. So on March 5th.
By the way, I started writing out all the topics that are left for us, in case you're wondering. Just to go back, we still have to do the second try for curve sketching. Come on, come on. For curve sketching right here, we have to do the second try for optimization and related rates. We got to do the first and second try for both of these still. Linearization and differentials and the slope field. Now, after that though, what you see after that is actually, we've done this already, Riemann sums. We quickly looked at trapezoidal, but we didn't look much into it. I'm going to go back to go over that. We did this already. We did the fundamental theorem, which is just integral with the limits at the top and the bottom. We did initial conditions. We did not do substitution method yet. We did total change, including distance traveled already. We didn't do these 3 here. So we really have 1, 2, 3, 4 things left for the whole year. That's it. So integration, what I want to do for integration really is this. I would like to have a test before the end of the 3rd quarter on integration, on the basic integration, okay, before the end of the 3rd quarter. Then to start the 4th quarter, we'll do the applications like volume. This is really tough stuff, and it's on every exam. And then from there we review. So the hope is to have at least 3 to 4 weeks of review. In the beginning of the year, my hope was like a month and a half. That's what I really wanted to do. But now we're at the point where if we finish by the middle of April, which is another month and a half from now, that gives us 3 weeks solid for review. We can really finish this whole year by the end of March, really, and have the whole month of April and a week in May to review, giving us 5 weeks to review. That's what we want to do. And what we're going to do in those days is literally this. We're going to take AP problems and we're going to solve them together. You guys can be working on them. I'm going to be showing you how to do some hints on them. And then what you're going to do some days is give you practice actual tests. I'll give you all the AP tests to practice on. I'll grade them for you and stuff so you can see how you're doing.
And they don't count.
Okay? We can count them, but we'll curve them so that everybody is... I haven't had some assessment in the 4th quarter, so you're doing that would be the way to curve it.
So you guys can fail, you feel so bad that you
No. You have to understand again, Kenny, right? A 3 on the AP exam is passing. A 3 is passing, believe it or not, out of 5. And a 3, no, of course not. But a 3 out of, the test out of 120 points, a 3 is more like a 35 out of 120. That's passing. So if you take a practice test and you get like a 35 out of 120, you could think of that as you pass the AP test. It really is what it says.
Do it one more time.
Okay? You have to do it, on the actual exam. Just
lie to your mom.
So, with that said, when do we want to do it this week, the other ones? So we got to do, and how do we want to do this? Do we want to do all 5 on Friday?
Friday.
Okay. So we're going to have curve sketching. You're not going to be here on Friday? Where are you going to be? Disney.
Disney.
Are you on Thursday? You're not here on Thursday? So it doesn't matter whether it's Thursday or Friday then? Okay. Because I was going to say we could switch to Thursday for you, but if it doesn't matter then, you just take it when you get back. Okay? So curve sketching, which is on the previous page. Please write these down. Curve sketching, and then these 4. Whoops. And then these 4. Okay? Curve sketching and those 4. Some people have trouble with optimization and related rates, so you might want to start looking at old stuff. What I did, by the way, is I spent some time in the last few days coming up with the problems out of your textbook. So if I can tell you right now how much, we have 5 minutes. Let me put those in right now so you can write them down also. I'll tell you the exact problems I want you to work on.
That's the one that you highlighted, right?
Yeah.
And the 2 before.
And curve sketching, the one before that.
Here it is. Okay. You know, EP got 4 stars.
Yeah.
For optimization, in your textbook, optimization was 4.4. Some practice problems for you are 4.4, examples 2, 7.
You got home. That was hilarious. I think they might have sent back to the You sent it to us in an email or like.
I'm going to post it later.
Yeah, post it.
Again, guys, I'm not telling you have to do them all, but these are problems that are good suggestions of examples.
I want to see the 2 worlds. Can we jump on it?
What movie do you actually
Like Disney.
or just for the lobster?
You gotta go tell the rest of them left.
Aren't those like
They're complimentary, supposedly. But they're complimentary revisits. Yeah.
You said you wanted to see Big Brother.
Yeah.
You know who had free tickets this morning? Chad.
Why?
I don't know, he just said that he had a free ticket. and he was all
Chad
like-
did?
Yeah.
What does Chad do? Like, he gets all these like sketchy
And I was
things.
like, I don't
For
want
free.
I don't understand that logic.
He had it for free, really?
Yeah.
I'm gonna play my birthday card.
He finally, after work.
Yeah, he's at like the office. He probably got it.
What are you doing? Where you got it?
Tuesday here. He works today. He works
Yeah.
No, I mean like use your own
Beautiful one.
You know?
You get it? You have it?
No, I didn't want it.
Probably get it.
For tonight, why would I go to this?
So why is it tonight?
He said, I don't know.
Guys, do you remember what this means if I put this here? I put QQ. Do anybody remember what QQ meant?
Quiz something?
Yeah, at the end of section 4.5, you're going to see like it's called quick questions or quick quiz. So some of the problems that are there are pulled sometimes. So for that one, I just want you to do example 2 for that one.
Hey, that's weird. The last two wow, that's Mr. Howell. You're cute or everything you said.
Okay, I'm working on the other ones right now still. I'm working on slope fields. There's not a lot of examples in your book on slope fields, but you all did really well with that. My recommendation would be to look at the packet I gave you, where we have the 4 AP problems we looked at, because today after school we're going to use that again. So after school today, make sure you have your slope field packet, which in case you want to see what it looks like, in case you want to see what it actually looks like.
No, oh my gosh.
Barbecue.
Really? I thought today was macaroni and cheese.
No, that's next Monday.
Cheesesteaks.
Remember this, guys? We started with this page. Okay? We got to these kinds of questions with the slope fields, and then we talked about families of functions. And these were where the AP problems came in. Remember all these problems for the AP? Remember how we didn't do, look at this, guys. Particular solution. Particular condition. Oh, who would have thought? Okay? So they give you the initial condition there, figure it out. So we'll talk about that after school today. Okay, after school today. Make sure you are there. Nobody should be missing today.
Wait. No, Justin's not here.
Right there.